Now it's time to dig a little bit deeper into the region of convergence for Laplace transforms. So our objectives for this next section are to be able to identify the region of convergence for a Laplace transform, and then to apply properties of the region of convergence. So let's look at our example that we had before, where we had two different time domain signals. We had h of t equals e to the minus at u of t, and h of t equals e to the minus at u of minus t. We had these two time domain signals, and it turns out the formula for the Laplace transform was the same in both cases. What was different? The difference was that the ROC was different. In the case of e to the minus at u of t, the ROC goes from minus a to infinity, and in the case of h of t equals minus e to the minus at u of minus t, it goes from minus infinity all the way to minus a. So you can see that these two regions of convergence, in fact, don't overlap at all. So this reemphasizes the fact that to determine a Laplace transform, that is, to describe a Laplace transform, we need both the formula and the region of convergence. So we formalize this in what's called a pole zero diagram, which we've been using a little bit informally in the last few lectures. A pole zero diagram is a picture of the S-plane, that is, the picture of the Laplace transform plane, the domain of the Laplace transform, marked with two different types of points. We put an x, where h of s blows up to plus minus infinity, and that's called a pole. And we put a circle, which sometimes we fill in, I think mostly I fill them in, and that marks a 0, where h of s is equal to 0. So the ROC cannot contain any poles because, notice, ROC means region of convergence. If h of s blows up to infinity, it's diverging, which means the integral is diverging. Therefore, the ROC cannot contain any poles, since the Laplace transform integral diverges. We're going to be focusing a lot on rational Laplace transforms, and a rational Laplace transform, we mean a ratio of polynomials in S. Right? So we have something that looks like this. H of s is equal to, on the upstairs, on the numerator, we have some degree k polynomial, for example, in S with coefficients a0 to ak. And on the denominator, we have the same thing with b0 to bl. We have a degree L polynomial. And then if we have these degree k and degree L polynomials, we can factorize them into a product of monomial terms. And this leads us to see that when s is equal to one of the alphas, we get a 0. And when s is equal to one of the betas, the Laplace transform blows up, so those are the poles. And this constant c here is to handle basically these two leading terms in the coefficient expansion. A major theme in this class is representing a signal as a linear combination of complex exponentials, or what we call an LCCE. And we've seen a lot of these already. For example, cosines and sines, by virtue of using Eulerizing, can be thought of as a linear combination of complex exponentials. And rational Laplace transforms come out of considering Laplace transforms of LCCEs. And that's because the Laplace transform is linear. So if I have an LCCE, which looks like some combination of exponentials with exponents beta, then if I swap the sum and the integral, I can see that I'm going to get basically Laplace transforms of each of these exponential terms, which each of these turn into a one root at one of the betas. Right? And so we gather like terms, we gather these terms together, we reduce this into one big polynomial, and we'll see that it'll be a ratio of two polynomials in S. So what is the ROC for the sum of two complex exponentials? So instead of considering this whole summation over many terms like in the previous slide, let's instead focus on something simpler and concrete. Let's say we have just two signals. We have e to the minus 2t u of t and e to the minus 3t u of t, and we add them together. We take the Laplace transform. So now, remember, we want the Laplace transform to exist, so we need S to be in the region of convergence for both this term and this term, both the s plus 2 term and the 1 over s plus 3 term. So the first one, we have a region of convergence that is the real part is greater than minus 2, and for the second one, its real part greater than minus 3. And since we need to converge for both, we get actually the intersection, which is just the real part of s greater than -2. So we can see here that we get a regional convergence that looks like this, and as you can see here, the ROC does not contain any poles. In general, of course, if we have two Laplace transforms with different regions of convergence, H1 and H2, with ROCs R1 and R2, then the summation is going to contain the intersection of R1 plus R2. Most often we're going to see that it's actually equal to the intersection, and the reason that we say that it's in general it's going to be only containing the intersection is because you could have this magical thing happen which is where one term cancels the pole in another term. You want to try to see an example of this. Here's an example of a Laplace transform where you'll get some cancellation, but in a practical sense this pole zero cancellation never happens. Because if you're actually building a system out of different components, and you have an H1 and an H2, and say you're putting it through an adder or something like that, you're never going to get the case where the poles are exactly where you built them to be, or you designed them to be, rather. So when you build a system, the poles are going to be, close to, maybe very close to where you designed them, but because of parts being slightly deficient and defective or variable and various other things, and there being noise in the system, for example, you're never going to get this exact pole zero cancellation. So it's really just sort of a mathematical artifact that we have to keep in mind, just to be careful. And that's sort of the difference. One of the important differences between considering a mathematical model and considering the real system is that we can sort of see sometimes the mathematical model shows phenomena which will occur in a real system, and sometimes it suggests that there is something that could occur, but we see practically does not occur. So what are the general rules for regions of convergence for ROCs? Well, the ROC is always made up of vertical strips that are parallel to the imaginary axis, and the ROC cannot contain any poles. So what do I mean by vertical strips parallel to the imaginary axis? Well, it means that we can have an ROC that maybe looks like this yellow region here, or we could have this strip here between these poles here, or we could have this region here, or we could have this region here. Right? All of these are fair game to be ROCs. They're vertical strips in the complex plane. If h of t is finite duration, and it's absolutely integrable, which, remember, this is just essentially saying that the system is stable. This is the same condition we had for system stability. Then the region of convergence is the whole complex plane. So ROCs basically have to look like these vertical strips. They can't contain any poles. They can be bounded by poles, and we have a special case here. So we call a signal right-sided if h of t is equal to 0 for t less than t0. So here's a picture of a generic right-sided signal. It starts somewhere and then goes off to the right. A left-sided signal starts somewhere and then ends at a point. So it's infinite direction in the left, towards the left, and two-sided signals have infinite direction in both directions. So if a signal is right-sided and the ROC contains, say, sigma 0, then the entire plane to the right of sigma 0, so this is the plane to the right of sigma 0, that is contained in the ROC. And similarly, if it's left-sided and it contains sigma 0, so here, for example, if sigma 0 is here, then we know this entire region must be in the ROC. So this is the plane to the left of sigma 0. And if h of t is two-sided, then we just know that it contains, say, if this is sigma 0, we know that it contains this strip. The strip contains this line, and it's two-sided, so it's bounded by some poles on either side. The other thing we can tell by looking at the region convergence and pole zero diagrams is special for rational Laplace transforms. So if h of s is a rational Laplace transform, then the region of convergence actually is always bounded by poles, or it extends to minus infinity or plus infinity. So that is one side of it there has to be a pole on one side, and then it either stretches off to infinity like this, or it goes from minus infinity to a pole, or is between two poles like this. And so if h of t is right-sided, then r of t is to the right of the rightmost pole. So if I go draw a pole zero diagram, I just have to look at the pole that's farthest to the right and say, oh, it's the right half plane beyond that. And similarly, if it's left-sided, then it's the left of this should be the leftmost pole. So here we have this leftmost pole here, and it's everything to the left of that. So try it yourself. Try finding the Laplace transforms of these various signals and find the ROC and draw the pole zero diagram. And I think if you do a couple of examples like this, you get a better feeling for how the pole zero diagram works, and looking at what possible ROCs there can be for a given Laplace transform in addition to the one that you find. So you can see where the poles are, and you can say, oh, there might be another region of convergence, so there's another signal which has the same formula for the Laplace transform with a different ROC. And we'll see a little bit more of that in the coming lectures.